So machine learning and AI has taken over different aspects of our lives, and it has also taken influence in many decision-making fields, including trading and investing. So today what we're going to do is we are going to discuss about neural networks trading and how we can create efficient strategies like this, which can beat the S&P 500 buy and hold returns, and pretty much create your own strategies using neural networks trading, or even improve on your existing strategies by adding a little bit of machine learning and AI. So let's start with what a neural networks trading is. So before that, this is our third video in this series in our YouTube channel. So a few weeks ago, we discussed about decision tree models. And then a few months ago, we discussed about the regression as well. So this is kind of complicated. That's why I kind of delayed it this much. Because neural networks is kind of a complicated aspect for anybody to understand and learn. So I'll try to make it as simple as possible so you guys can understand it. So neural network is just like the way your brain functions. So it's like your brain has got neurons. So when you see a number like 3, the brain looks at the number 3, identifies the curves and everything, passes on the signals, and makes a decision saying that, hey, it's 3. So that's pretty much what neural networks does, the machine learning model does. So when you get an image of a cat, the neural networks can identify that it's a cat through different kind of training regimes. So there are different kinds of neural networks. So the most basic one is a feed-forward neural network. So that's used for like image classification. So let's do this example here. So let's assume that you feed in an image of a cat, and what happens is that there is the input layer, which is the cat picture, and then there are like hidden layers, and each hidden layer will have certain information, certain weights added to it. So that weights will be initially set as kind of like random weights, and then it will identify it as something. So let's assume that the initial identification is like a cheetah. So obviously there's an error because this is not a cheetah, this is a cat. So it creates kind of like an error term like I, and then it goes back into that weight area, and then it kind of adjusts the weight. So the different weights, there are weights here, there are weights there. So there are weights everywhere, and each weight is going to adjust, and then it's going to go forward again, and then find out whether it's a cat or a mouse or a cheetah. And again, if there's another error, then again it creates a new error, and then again it goes back and does the whole process over and over again, unless and until it finally gets the fact that it's a cat. And then you've got really a neural network model here. So what I just said right now is basically a simple example of a feed-forward neural network. So the initial things here, those are the input layers. So I'm just going to mark it as I, and then this is the hidden layer, and then finally that is the output layer here. So you've got the input layer, hidden layer, and output layer. So you know the number of times this process goes over and over again. That's called iterations, or in other words, epochs. So in this example, we have just taken a cat and then a picture of a cat and finally concluded that, hey, this is a cat. And this whole model is called feed-forward neural network. Now, on the other hand, in case of recurrent neural network, we've got a different thing. So this one doesn't have a memory. So once the model is created, it kind of identifies that a cat as a cat. So on the other hand, when it comes to stocks, or like, for example, predicting the next word, you have essentially what is called recurrent neural networks. So recurrent neural networks' fundamental advantage is that it's got a memory advantage. It can remember things. So for example, it's used in a sequence of data, like for example, stock data. So it has got prices of yesterday, day before yesterday, and all those things. So you've got like a sequence or like a sentence, like I like to drink coffee. So we can use that to predict the word here, coffee. I like to drink coffee. So the thing that we said, when I go back from the cat after the error and check back the weights, that's called back propagation. And then after that, when it goes forward, it is called the forward propagation. So there's I've created a simple picture here, got it online. So here you can see the back propagation. So first, initially, it goes to the input units and it adjusts the weights of the hidden layers. These are the hidden layers, hidden units 1 and hidden units 2. So here we've actually created a simple one with just one hidden layer. And here you can see there are multiple hidden layers. There's like 2 hidden layers, and finally creates the output. And then the output goes back to create the error term and then adjust the weight from the hidden and the inputs, and then it goes back again. So that's called back propagation and forward pass. So the fundamental difference between recurrent neural network and the normal feed-forward neural network, it's got back propagation not only through the hidden layers, but it's called back propagation through time. So that's through the hidden states. So it's got like a sequential time step. So let's take this example of I like to drink coffee. So in time t1, the first word you get is I, and there's no previous hidden state, and the current hidden state, then there's a new hidden state created, and that's h1. And then during the next time step, you have got the word like, and you've got the previous hidden state h1, and then you've got a current hidden state h2. So it has got information from the previous hidden state as well. So that's how it has got memory. And then in time t3, we've got 2. And then it got the previous hidden state of h2, and then it got a new current hidden state of h3. So again, it is carrying over that memory which the previous situation of a cat didn't have. So in this case, because of the back propagation through time, the recurrent neural network has got an advantage, and that is the whole idea of memory advantage. And finally, in t5, we don't have any more input word, and we've got the hidden state of the previous one, h4, and based on that h4's data, we make a prediction that it is coffee. So just like the prediction is done for coffee, you can actually use it to predict the stock price data. So instead of T1, I like to drink, it can be price of yesterday, price of day before yesterday, and things like that. And you can use different kinds of input. Instead of the price, you can use the RSI, you can use the volume, and you can use the target as the 5th day return. So here's like 1, 2, 3, 4, it's like the 5th word, right? So instead of the 5th word, you can actually use the target return as the 5th day's return. So I've given like a trading example here. So here we've got the time T1, T2, T3, T4, T5. So input, we've given the price of the first day and the RSI of the first day, and the price of the second day and RSI of the second day. So each time in the hidden state, the memory is being stored and the new information is carried over, and that helps us to predict certain things in the stock market. We can predict whether the market is going to be a positive or a negative by using all the RSI data and the price data of the past. So the recurrent neural network or fundamental neural network has got certain problems. The fundamental problem is that it's got a computational issue. So you need lots of computational power, unlike decision tree or regression where we can actually create. So in our strategy, we actually use Quant Connect, and they don't use GPUs, they use CPUs, and still we were able to create one. But when we go to more complex one like LSTM, it takes a long time to test it. So even in Quant Connect, I've seen like 15, 20, 30 minutes for it to actually load up. And there's a time after a certain time, it kind of shuts down because, you know, it's too much load for the computer to actually run the strategy. But even then, Quant Connect is pretty good in executing these machine learning models. But in future, what is going to happen is that you're going to have GPUs and everything to make the models even more powerful. So in this specific strategy, we created a 64 as the memory vector. So we can also decide on how much the memory vectors are. So we can create more complicated memory vectors, like from 64 to 128 to 256. So in the strategy, we use 64. So it's much more faster to train the model. And then we can do lots of kind of hyperparameter tuning. We can change the input features. We can change the epochs, that's the number of iterations that the model used to train. You can use the hidden vector size, that's what I've said here. And you can also adjust things like learning rate. So these are all like more complicated hyperparameter tuning, which I'm not going to explain it here, but I have explained it thoroughly in our course. So this basically is covered in our machine learning and AI course, including this strategy. So we've actually got 8 machine learning and AI strategies. We have also got combined machine learning strategies where we combine recurrent neural network with that of regression and things like that. So that's give us a fundamentally better edge. So we've used AI in even portfolio rebalancing, also in combining multiple models, and after each section, each model that we discuss, basically we've discussed 5 models here. We've discussed regression, decision tree, support vector machines, recurrent neural networks, and long short-term memory. And after each of these sections, we've got a strategy. And after each strategy, we've got a quiz as well. So a quiz would be something like this. So for example, this is a recurrent neural network quiz. So these quizzes are created so that you understood what's being explained, so that you can create your own recurrent neural network strategy. And you'll have the strategy code and the lecture and all those things. So we've also got different kind of strategies as well. All these strategies has beaten the SPX CAGR to maximum drawdown ratio. That's what we are aiming for in our course, or any strategy. When you create, the fundamental comparison measure is the SPX CAGR to maximum drawdown ratio. So we also discussed the applied Markowitz portfolio optimization to AI as well. So Coming back to this lecture, so one of the advantages of the neural networks we can apply it anywhere. So imagine you have like a strategy which is performing well. You can actually make it perform even better or reduce the drawdowns and things like that using neural networks. So going back to the recurrent neural network, RNN has got a fundamental problem, and that is the vanishing gradient problem. So it tends to forget stuff that is kind of like in the past. So for example, when you read a book, let's say you're reading Stephen King's The Stand, which is like really, really big. So you tend to forget some of the characters because there are lots of characters. So just like human beings, we forget stuff. So the neural networks also tends to forget stuff, and that's because of the back propagation errors and the weights and things like that. So in order to avoid the situation, LSTM has got a thing called forget gate. So along with the hidden units, there will be a forget gate which kind of takes care of the problem of the things that they forget, and it will take into consideration the important things in the past that has to be remembered. So that helps us improve our result for the LSTM. But the problem with LSTM fundamentally is that it is extremely computationally intensive, that it will take a while to backtest this strategy in LSTM. So let me get the LSTM strategy here. This is a strategy we did for the LSTM. We've done the portfolio optimization, rebalancing using the LSTM machine learning model AI. So these machine learning model AIs, like neural networks, not only for you to create efficient strategies, it can also be to rebalance a portfolio. So imagine you have like a value investing portfolio and you need to adjust the allocation of the portfolio. So you can use the machine learning model to actually allocate how much money do I need to allocate to SHY, how much money do I need to allocate to GLD, SPY, or TLT, and get superior returns while minimizing the drawdown. So these are some of the things that machine learning models like RNN, LSTM, and many other things can use. It's just not for entry or exit conditions. It can be to improve your existing basic quant trading strategies. It can also be to rebalance a portfolio. So now let's go back and discuss the code of the recurrent neural network. Okay, so as you can see, so I have imported the libraries NumPy and scikit-learn. So there is a fundamental Python library for neural networks in LSTM. For this specific strategy, for the RNN, what I did is that I actually created the equations myself so that you guys can understand how the process is done and if you want to make any changes. The advantage of having libraries is sometimes it can be you don't know what's happening inside. But it is easy to use. You just have to import the libraries and actually run it. But sometimes it's also good to know what happens inside of it. So I actually created the code myself for the recurrent neural network. So you've got the start date and end date. So that'll be our testing data. I've set the cache. I've taken values of RSI, MA, and the 200. So if you don't know anything about Quant Connect or Python, I think the first thing you could do is visit our YouTube channel and go through algorithmic trading in Python, 0 to hero. And once you're done with that, you can actually visit our Quant Connect full tutorial as well. So you're kind of up to speed on how to handle Python. And then you can come here and it'll be easy for you to understand. So these are kind of like the prerequisites that you will need to understand a certain level of Python so you understand what the code does. We're warming up the data. So it warms up 200 days, and then we are looking into the parameters. We are looking into how many days we need to look back. So remember, we did T1, T2, T3, T4, and T5. So that could be like 5 look back periods. So in this case, we're doing 10 look back periods. We are doing a feature count. So that could be anything. It could be a price change. It could be an overnight gap. It could be a volume change. It could be an RSI. It could be anything. So it's kind of up to you on what to choose the input features are. We're not going to show the input features that we have and the entry or exit conditions that we have. But for the people who have done the course, you have access to that specific thing. So you've got the hidden size. So remember I said the 64, 128, the vector sizes, the memory vector. So that's kind of dictated here. Then the learning rate is dictated. And then initially the prediction is set as 0 because that's what we're going to find the value. Is the prediction going to be positive or negative to go long or short? We've used the standard scaler to scale our numbers. So people who don't know standard scaler. So basically when you get different data, so for example, RSI can give you a certain number, but volume can give you like 100,000. So the RSI might be like 30 or something. So you see all these complete variations of these numbers. So in order to make those numbers kind of be comparative, that's why we use standard scaler. So standard scaler helps us convert these numbers to analytical ones so that there is no massive discrepancy, because a bigger number can affect the model completely. So we don't want that kind of situation. The volume might take over instead of the RSI number. So in order to do that is why we use standard scaler. And then we're going to use initialize RNN function, which is something that I created, and also the train RNN function. So the initial ones are the ones that we decide on the weights, and then we also decide the biases. So initially, as I said before, the weights, I think I did said before, so initially the weights are set as random. The first time it goes, and then when you get the error, then the weights are adjusted accordingly. So in this case, we've actually set up the random function and created the weights, and also we created the bias, and then finally we train the model. For training, we're using 2000 to 2009. So I've discussed this in our previous videos about training and testing data. So we're using training data from 2000 to 2009, and we are testing it on 2010 to 2024. You can change this. You can update it as you keep on going. You can actually do it from, I don't know, 1990 to 2000, and then train that on, test that on 2000, 2010 instead as well. And then we're going to get an array which stores the features and the targets. And the features are going to be got from our get features from history, wherein we can feed in the input features, whatever input features you want. And then obviously there is a target. And then obviously we're going to scale off it the features, and then we're going to transform the features. And here is the epoch, so the iterations, the amount of iterations. So I can increase these iterations to higher number, but again, it is going to come with a higher computational power. And sometimes Quant Connect might not be able to handle it if you're given like too many epochs. And then we're going to find the epoch losses and all those things. And here is the forward propagation and also the backward propagation as well. So here you can see we have used the self.backward function here to find out the epoch loss and the hidden state and target and the prediction. And then here is the forward propagation. We've got the hidden states here. It's an empty array. And then we append the hidden states. We add up the hidden states. And we can see here we have actually put in the weights and also the biases. And we are going to return y and also the hidden states as well. And then with that information of the hidden states and the y, and y underscore predict is the value that we are trying to predict, we feed in the weights, and then we do the backward propagation, and we get the biases in weights, and then we keep on updating it because it has gone through different kinds of epochs, right? So we've got the learning rate, again, it's being adjusted. So finally, we have got the complete model of the backward propagation. So we've got the backward propagation and we've got the forward propagation, and it's being trained. And then comes a def on data, which I'm not going to go too far because that's basically the entry and exit conditions, and also the get features, the input features as well. So those are available for our members, and they can access it in their specific strategy code section. Let's go through the results of this and see how it has performed. Okay, so we have actually included the commissions as well. So all our strategies comes with commissions included. So let's go to strategies. Strategies performed on the SPY, as you know, as you've seen it in the codes. So we've got a compounding annual return of 9% with a drawdown of 18%. So let's do the calculation. So the S&P 500 CAGR to drawdown ratio. So CAGR is 10. And we are dividing it by the drawdown, maximum drawdown, which happened in the 2008 financial crisis. That's 55. So we've got a ratio of 0.18. So unless we've got a strategy which is above that, we can't go ahead in executing that strategy. So in this case, it's 9% divided by 18.3. So we've got a ratio of 0.49, which is pretty impressive. So the S&P 500 buy and hold CAGR to drawdown was 0.18. So the advantage of this is we can apply a little bit of leverage. You can apply like a 2:1 leverage and get like an 18% CAGR, and still the drawdown will be just like 36% or something like that. Still, it won't beat the maximum drawdown of an S&P 500 buy and hold. So there are lots of things we can adjust to it in these numbers, and we can make the strategy improve by adjusting the epochs, or adjusting the input features, or changing the input features, or adjusting the hidden size and things like that. So there are lots of things that we can play around with in the input features or the hyperparameter tuning, which we have explained thoroughly in the course. And that is one of the challenges that you have. Like, we give you a condition, these are things that you have to change, and these are the things that you can improve the strategy. So this is the RNN strategy, and you can actually improve this strategy as well by combining it with different models. So let me go through some of the performance of our machine learning strategy of that training data. So I can see different models here. So S&P 500 ratio 0.18. So our linear regression model has 0.32, decision tree 0.45, support vector machine 0.44, recurrent neural work 0.49. There's a combined model of 0.39. There is the combined AI model of 0.45. There's another decision tree of 0.1. I think I haven't put in the LSTM, so I think it might be there below here. Long short-term memory. There you go. That's a long short-term memory. That also has done spectacularly well. Then we have got the RNN regression, which is combining the RNN and the regression. We've also got the RNN plus support vector machines as well. So there's lots of growth prospects when it comes to application of machine learning and AI to trading. And these are just the fundamentals. We are just taking baby steps. So I think within like a 2 to 3 years time frame, people will be discussing more about what kind of machine learning models to apply for a specific trading strategy. Can we apply it on a momentum trading strategy? How can we change the portfolio? How can we create multiple strategies using neural networks? Can we apply neural networks on multiple quantitative trading strategies to rebalance the portfolio? So the amount of growth prospects for this is very huge. So hope you guys enjoyed the video. Let me know you understood everything. Let me know if you have any confusion in any of these things. I'll be happy to help you. Thanks for watching. Bye-bye.